Okay, so we were doing this problem right before lunch, and we got down to negative infinity over 0, which is not indeterminate, which means technically I should not have started with L'Hopital's rule to begin with. Actually, I haven't done L'Hopital's rule yet. I just did the natural log. But anyway, we are now at this point, and we're trying to figure out what infinity over 0 is. And if you remember way back to our infinity or our limit days, we learned that if you have a number over 0, like a finite number over 0, that would blow up in either direction, or if both sides are going in opposite directions, you would say does not exist. Do you remember that? Okay, well, if my numerator is not just a constant but infinity, then this is going to blow up even bigger, right? So this answer right here is either going to be infinity, it's either going to be negative infinity, or it would be non-existent. However, if you are coming from one side, you will either be going up or down, so it's not non-existent. We only need to determine if this is going to be a positive or a negative fraction, and as x approaches 0 from the right, ln x is going to negative infinity, x would be positive, so that's like a positive 0, which means this answer will be negative infinity. Okay, so where I was going right before lunch, so I was saying that even though it wasn't indeterminate, this is not a lost cause. We can still use this work because I got an answer to my altered limit. All I have to do is undo my natural log. I never did L'Hopital's rule, but I could still use this answer to answer the original. So therefore the limit as x approaches 0 from the right of x to the 1 over x, well, I have to undo the natural log by doing e, and we have to figure out what is e to the negative infinity. You should know that! That's 1 over e to the infinity, which would approach 0. And there's your answer. So apparently 0 to the infinity is 0. It's not indeterminate, it's 0. Good on 49? How was lunch, by the way? Was it lunchy? Huh? Oh. Where'd you take them? Did you get good money? Oh. Alright. Alright, so let's go back and see what you can do with 51. Did we do 51? Was that an example that we did yesterday? We did one example of power indeterminates yesterday, or Tuesday. We'll just do it anyway. Okay, so let's look at 51 then. Copy over. Okay, so I'm going to plug in infinity, and we get what? Infinity to the 0. Is that indeterminate? Again, I don't know. We'll see. So I'll alter the problem to find out. And if I do the natural log, I'm going to go, we're pretty smart in here, aren't we? If I insert a natural log, that's going to become 1 over x, natural log x, which is just ln x over x. Oh, this is a nice one. This one's really nice and clean. So ln x over x as x goes to infinity is indeterminate. That's infinity over infinity, so that tells me that I need to do L'Hopital's rule now, right? By the way, if you are absolutely 100% confident that this is indeterminate, then you don't need to bother checking this step. If you start indeterminate, you will remain indeterminate, but as I've shown, I don't know my power indeterminate, so I always verify at this point before I lope it. So now we will lope, given me x approaches infinity, 1 over x, no! Over 1. And 1 over infinity is 0, but that means that the limit as x approaches infinity of x to the 1 over x, if I undo that natural log I threw in earlier, is e to that answer, which is 1. We good? Bad? Ugly? Yeah? And just remember, before you L'Hopital it, you've got to turn it into a fraction. Some level of algebra, you've got to turn it into a fraction, and then you can loop it. Good? Alright, I'm going to freeze the screen. Y'all see what you can do with 53, and I'll work out 53, and we'll see if we can come to any kind of an agreement. Okay. Alright, here's what I have so far. I haven't finished it yet. But I got 1 for the answer to my altered limit. Did we get 1? And that means the answer to my final limit, x approaches 0 from the right, of 1 plus x to the 1 over x is e to the 1th, which is e. So finally we got an answer that wasn't 1 or 0. What do we think? What do we think? Okay, that brings me to some special limits that probably you should memorize. And they are all limit variations of e, limits with an answer of e. Because we're gonna need to know these limits when we get into the very last unit, and I will review them again. So limit definitions of, that's okay. Limit definitions of e. Remember, e is approximately 2.71828182845904523353. So limit definitions of e, the one we just did. Limit as x approaches 0 from the right of 1 plus x to the 1 over x does indeed equal e. That's one that we're not going to see as much. The one that we will see more often, and I'll spare you the proof that this is e. By the way, to prove it, all you would do is lope it and show that it does give you e, right? You will more often see this one. The limit as x approaches infinity of 1 plus 1 over x to the 1 over x, to the x power. That is also going to give you an answer of e. And that second one is the one that we'll see more often because our very last unit that we do is dealing with infinite sequences and series. And we're going to be looking at those as we go out towards infinity, as we get to the end of the series. And so we'll be seeing that this limit a lot towards the end of the year. I am going to show you a couple of children to broaden these limit definitions. So if it's 1 plus x to the 1 over x, that is just e. But if you have coefficients, if you have 1 plus a number times x to the b over x power, that answer would be e to the a times b power. And this one down here, the bottom one, which is the one that if you are going to commit one of these to memory, this is the one to commit to memory. 1 plus a over x to the b x power does equal e to the ab power. And so those are two limit definitions of e that they show up enough that it's okay for you to memorize them. If you don't have them memorized, the mechanism for solving it would be to lope it. Take the natural log and lope it, and you work it out that way. So I'm not going to say it's absolutely mandatory that you memorize it, but come that last unit in about 5 or 6 months, we'll see this enough that you're going to get tired of loping it every time. You'll eventually learn it, even if by accident. We good? We good? All right, there was one more. One more. Oh, crap. This thing moved to the other monitor. Why is it sticking a firecracker? Okay, so I'll just arrow back here. Let's look at 55. See what you can do with 55, and we'll go over that one in a minute. Whoops, you go away. If you want to do this, you can take constants out of the limit. I don't know if this is going to help me or not, but I know that the limit of 3 times a function is the same thing as 3 times the limit of the function. So I'm going to get that 3 out just to make the inside a little bit cleaner. Just don't forget that it's out there. So when you ultimately get the answer to this, and you do e to the whatever to find the whatever, you have to remember that we're doing 3 times that answer, and just don't forget that there's a 3 hanging out there waiting to be dealt with. So here's what I have. I ended up ultimately with an answer of 3. Did we get that? You okay? And so again, I had to remember that 3 was out there, and then I just worked it out ignoring the 3. I did verify right here that it was indeterminate. 0 times infinity is indeterminate. The over 2 doesn't matter. And then you lope it and clean it up. You get 0 for the original, and that ultimately turns into 3. I'm sorry, 0 for the altered one, and then that ultimately turns into 3 for the original. Good on 55? Yeah. So how are these coming? Feeling okay about L'Hopital's rule? Yeah. I believe that, let me look at my calendar here. Let's see. Our test is next week, I think, and I'm right. L'Hopital's rule is the end of fair game material for the test next week. And so it's kind of a big test. It's your applications of derivatives. That will be the increasing, decreasing stuff, curve sketching, L'Hopital's rule, optimization, related rates, the theorems, mean value rules, extreme value. Um, what else? What else? It's a fair amount of stuff coming up on this test. Um, so that's coming up next Thursday. And in the meantime, we will, well, for the rest of today, we're going to talk about free response questions. And homework tonight will be starting antiderivatives. So we're about to start going backwards. I'm going to give you the derivative, and we work backwards to get the function. Um, so if you don't know derivatives, you better learn them because we're about to do them backwards. All right, so let's look at what time do we get out of here anyway? Huh? 25? I guess I could look at my schedule over here. What class is this? Who are y'all? 12:25. Y'all were right. I thought y'all were liars. Okay. Looking at some of these free response questions, and I don't know where I want to start. I'm thinking let's go back and look at, did we start this one, 2018? There was this one I gave you the other day. Not the one I just gave you when you came back from lunch, but I gave y'all this one the other day. And I think all we got to, if I'm not mistaken, I think the only one we got to was number 4. I'm sorry, part A of number 4. Is that right? We did B as well? Okay, well, actually, I could go back to the notes. We will not do C. We do not know how to do trapezoidal approximations. That is coming in the next few weeks. So let's go back to Tuesday, and let me just pick back up on part C. Y'all are third period. Oh! Did we do them at the beginning of class? Was it Monday? There it is! Okay, so it does look like we finished it. Now, I don't know if we I think I finished it very hurriedly. I think it was right as the bell was ringing. So we did I do remember doing part A. And don't forget that if you're explaining derivative values, go back to the context of the problem. The height is increasing, and always include your units and your numbers. Explain why there must be a time on 2 to 10. Oh, we didn't finish it. We didn't finish it. Because this is what I did. I assumed that since they said the interval was 2 to 10, that I would use the mean value theorem from 2 to 10, which is usually a safe bet. But when I applied the mean value theorem on the interval 2 to 10, I actually ended up showing that, and I'll grab this, that the slope would have to equal not 2, but whatever this thing, 15 minus 1.5 over 8. And so this is where we are. Whoops. This is where we were. And this, I was shooting for 2. That's not equal to 2, which doesn't mean we chose the wrong approach, but somebody did say, and I remember this, somebody said, oh, well, you just have to find another interval. And was it between 5 and 7? Is that what that arrow is up there? And so since 2 to 10 didn't work, then we have to fish around inside the interval 2 to 10 to see if we can accomplish the slope we want. And it does turn out that if you go from 5 to 7, you're, oh, that's up 5 halves. That's not even it. It's 3-5? Okay, I'm going to have to wipe that out. You're gone. You're gone. If you look from 3 to 5, we go up by 4 on the height and up by 2 on the time. So there is the interval we're interested in. So that failed. So mean value theorem, I'm going to ignore that. And we are continuous and differentiable on the interval 3 to 5. Therefore, mean value theorem says that f, oh, this is h prime of c is equal to f of 5. It's h, not f. H of 5 minus h of 3 over 5 minus 3, which does equal 6 minus 2 over 2, which is 2, somewhere, we don't know where, somewhere on the interval 3 to 5, which is inside 2 to 10, so that would be good enough. How's life on that one? Good? Bad? All right. Let's pick up on part D. I think I'm going to need the table. Let me grab the table. Let's see. Height is twice differentiable. I'm not going to bother re-grabbing the paragraph. Actually, I will re-grab the paragraph. I lied. So let's grab that. And let's look at part D. Lots of words. Lots of words. Okay. Oh, geez. Okay, so height is our twice differentiable function. Holy cow. Who created all this stuff? Okay, so the height of the tree can also be modeled by this function. So they've brought you another function that is also modeling the height of the tree. So you could kind of make a note that this is probably pretty close to the function h. It might be an approximation, or h might be an approximation of this. I'm not sure. But they both represent the same thing. X is the diameter of the tree. Ooh, so they changed this. No, it's not a function. Okay, you know what? I'm going to get rid of that. Because x is diameter. This is a function of diameter, where h is a function of time. So I can't say that they're approximately the same thing. Let's see. When the tree is 50 meters tall, okay, so now they're defining the height to be the function g. So they're telling you that we're looking at a point in time when g is 50. The diameter is increasing at 0.03 meters per year. So I would like to say d dt is 0.03, and I guess I'll put meters per year to keep track of time. But it's not d dt, because they were weird. They said that the diameter is x, so that's dx dt in the context of this problem. So dx dt is 0.03. That is increasing. According to this model, what is the rate of change of the height? What is the rate of change of the height? We are finding the change in height. That will be dg dt at the time when the tree is 50 meters tall, which we already have at the time when g is 50 meters tall. So what do you think? What do you think we'll do? Well, we're going to have to find, dg dt. So if g is the function 100x over 1 plus x, I'm going to have to find the derivative of that with respect to time, which would be a quotient rule. Should we do quotient rule, or do you want to move the 1 plus x over and product rule? What do you think? I prefer the product rule over the quotient rule, but we are trying to find dg dt. So if I move stuff over there with the g, then I'm creating more work for me to solve for g later. So I would rather deal with the ugly quotient rule and just leave the dg alone. So low d high is going to be 100 dx dt minus high 100x. D low would be 1 plus, the derivative of 1 plus x, which will be dx dt, all over low 1 plus x squared. What do you want to do? Do you want to go ahead and plug in? Our options are plug in, because we do know what g is. Oh, g doesn't come into play. Ah, crap. We don't know what x is. We do have dx. We know dx is 0.03. I have to find x. How am I going to find x? Yeah, well, if I know what the height is, I could find x by plugging 50 in for that. So find x. 50 is going to equal 100x over 1 plus x. So that's 50 plus 50x is equal to 100x. X is 1, right? Oh, that's sexy. Very good. So now I have something to plug in for x. I know that dx is 0.03. So my answer, dg dt, is going to be 1 plus 1, which I think is 2. 100 dx times 0.03 minus 100x, that will be 100, times dx, which is 0.03, all over 2 squared. What are we thinking? Are we okay? And then what's the very next thing you'll do? Very good. You write the units and you quit. Because I can see myself screwing that up somehow. 100 times 0.03 shouldn't be hard. It's 3, right? Right. Then I think the final answer is 3/4. So it cleans up fairly nicely, but you don't get more points for cleaning it up. We are now done with the calculus. It's all arithmetic. G is the height of the tree, so that will be measured in units of meters, and the time in this problem is measured in years. So I would stop right there. Clean it up if you want to, but you better clean it up correctly because you lose the point if you mess it up. Good, good? Good, good. You have plenty of chances to show off your cleaning up skills when you do the free response. Oh, when you do when you do the multiple choice. All right, let's see. I think I want to. This is a good one, but the only thing I don't like about this one is this is strictly related rates. There's nothing else to this one. This is related rates and only related rates. I think I may come back and look at that one. I am going to look at, so I chose several problems here. So the 2018 problem, the bottom cone one, and then I also gave you one. I think I'll look at, you know what, this is a good one. Let's do this one. This is from the one I think I handed out Friday. It was titled Related Rates Quiz, but it's not a quiz. It's just related rates problems. And I did just say I didn't want to do that cone problem because it was only related rates. And now I'm about to contradict myself because we're about to do this one from 1987, which is only related rates. But it does have a good question that I like in part C. So let's look at this one. Let's look at this one and see how much we can do here. And I'll copy this picture. That was a drawing I did on a computer. I don't know what the picture looks like on the actual test. Let's go current page. So we have a trough. It is 5 feet long. Vertical cross sections are isosceles triangles. And the base is 2 feet across the top and 3 feet deep. Water is being siphoned out. Big word. Not really big word, but important. Water is being siphoned out at 2 cubic feet per minute. What did they give us? That's a rate of change. It's something per minute. That's the derivative of what? That's volume. Now, they did not use the word volume, but you should be able to gather volume from the units. 2 cubic feet per minute, right? But be careful. It's not 2 cubic feet per minute. What is it? Negative! It's being siphoned out. That volume is decreasing. That volume is decreasing. I have a typo here. At any time t, let h be the depth of the water and v be the volume of the water. I said let h be the depth of v be the volume, which doesn't make any sense. But so h is the depth of the water, so I think I'm going to include, by the way, that little rectangle is supposed to represent the surface of the water. So that is the height of the water. Find the volume of the water when the trough is full. They did not give you a formula for volume. By the way, this is not calculus either. This is just the volume of the trough. How do you find the volume of a prism? Very good. It's area of the base times height, right? This prism, the base is the triangle. Your bases are the sides that are congruent and parallel. So triangles, that'd be 1/2 the area of a triangle, which is base times height. So that's the area of the base times the height of the prism, which is the distance from front to back, which I cannot use h because I just used it for the triangle. I'll call it L for length. I guess you can say D for depth. Oh, but then I'm going to get it confused with depth of the water. Yeah, let's go L. Right. But what's so nice about this? About my volume formula? With regards to the water, B is that measurement, H is this measurement, and L is the distance from front to back. What's nice? Very good. Front to back does not change. In a related rates problem, you want to identify anything that is constant. Does not matter where we are as far as filling up or emptying this trough. The distance from front to back is always 5, so we get rid of the L and put a constant in its place. Anything that changes needs to be given a variable. So the volume of the water overall for any point is going to be 5/2 BH, right? So there's the formula for volume. But when it's full, my height is 3 and the base is 2. So my volume when full is going to be 5/2 of 2 times 3, which is 15 cubic feet. Always include units. We good? Make a little note, that's full volume. And let me go back and grab question number 2B. 2B. Or not to be. What is that, 1984? I think so. War and Peace? Ah, Hamlet, that's right. I knew it was one of those Edgar Allan Poe things. Alright, so what is the rate of change in the height, which is the height of the water, at the instant the trough is 1/4 full by volume? I'm going to see if I can move this up here. I'll move that up and shrink it. We can still read that, can't we? You have it in front of you anyway. Alright, so B, we're looking for dH dt. We're trying to find dH dt when the trough is 1/4 full by volume. So now we get to factor in what we know about the full volume. So we're looking at a point in time when the volume is 1/4 of that, and 15 divided by 4 is 15 divided by 4. I'm not going to worry about decimals, and I definitely don't want to do mixed numbers. If you write 3 3/4, I might bite you. That's like 5th grade stuff. Good. So now we're back to our volume formula, which is 5/2 BH. That's the volume of the water at any point. And we're looking for dH dt when volume is this. Ooh, interesting. What do you want to do next? Yes, the triangle thing. Because if you dive, and I almost did this, I'm going to erase this. If you dive straight into the derivative, you're going to end up with this. It is a product rule, and hopefully you would do the product rule correctly. You'll end up with that. And the only information we have is that the volume is 15/4. We don't have H, we don't have B, we don't have dB, we don't have dH. All we have is dV, right? And so when you have that many unknowns, very frequently you can adjust the original equation to knock out some variables. And this is a case, and I did tell you, if you ever see triangles nestled inside triangles, you almost always will take advantage of similar triangles. So I see my water right here creating this triangle. That triangle is going to be similar to the triangle that is the end of the trough. So we'll set up similar triangles with those, and those similar triangles will allow me to turn B into H or turn H into B. If this thing ever goes back to my pen instead of the highlighter. Come on, buddy. Oh, Paul. Oh, there he goes. Okay. So my base to height ratio is always going to be in the ratio of 2 to 3, which means 3b is equal to 2h. And now I have to decide which variable I want to keep. We are looking for dh, and so I want to keep h in my formula, which means I need to substitute out the b. B is 2/3 h. I now take this, replace the b with that, and I get a better volume formula of 5/2 times 2/3 h times h, which cleans up even more to 5/3 h squared. And there's my new volume formula. We good? Now I'll do the derivative. Now my dv dt is really nice. dv dt is 10/3 h dh dt. I know dv is -2, is 10/3. I don't know h, and I'm looking for dh. So I now have to find h. And when you go back to look for unknown variables, you very frequently go to the original formula, which was volume is 5/3 h squared, and we were looking at a point in time when volume is 15/4. So 15/4 is equal to 5/3 h squared. That cleans up to 9/4 equals h squared, and h is 3/2. We good? Evil? Maybe. A lot of work. This cleans up really nicely to just 5 dh dt, so I'll divide by that 5. You get -2/5 is dh dt, and units for height would be feet, and my unit of time is minutes, and there is our answer to part B. How's life? Wonderful. Number C. What is the rate of change in the area of the surface of the water, which I have shaded, at the same instant when the trough is 1/4 full by volume? And I told you the other day, they typically, when you are piggybacking on previous parts, they typically make sure you are looking at the same point in time, so we don't have to recreate any work. Same point in time, so everything I have done so far can be imported and used in part C. First thing we have to do is decide what formula are we going to use. We need the area of the surface of the water. What shape is that? It's a tough question. We're looking for dA dt, and area would be the area of a rectangle, which we typically want to say base times height, but I'm definitely not going to do that, because height is already defined to be the height of the water, not the height of this rectangle. So B is the short distance. Oh, but here's the cute part again. The distance from front to back is a constant 5. So the area is 5b. Good. So there's our formula. Really nice. What would you do next? To the volume? Oh, no, you're making this really hard. We're not plugging any, we're ignoring volume. We're looking for dA dt. Is anybody thinking find the derivative? Not a bad thought, but you might hit a wall here because the derivative is going to be 5dB dt, and if I'm trying to find dA dt, I need to plug something in for dB dt. Do I have that information? I don't. So now I have a second problem. Before I can solve this one, I now need to find dB dt, which we could do. I'm not going to. because I know that B is 2/3 h. Why don't I plug that in here and give myself a variable that I already have a bunch of information for? We're at that same point in time. We're still a quarter full by volume. So everything we have up here I can use. Let's change my area formula to 5 times 2/3 h, which would be what, 10/3 h. Now when I find my dAdt, it's going to be in terms of something I already have. The derivative of 10/3 h is 10/3 dH dt. Do we know what dH dt is? Yeah, that was our answer to number B. That'll be 10/3 times negative 2/5, which is, oh, what am I, who cares? Feet squared per minute. Yes! I was wondering if anybody was going to ask that. Okay, if you, yeah, if you miss part B, then technically you miss part C. When they are reading the AP exam, there's something called reading with the student, which means if you mess up part B, but you have something that's reasonable, and that's the kind of ambiguity-ish part. If you have something reasonable and you use it correctly in a later step, then you can get full points. And so we kind of say, okay, because we're restarting, you did everything perfectly in C, you made a sign error, so maybe you got 2/5 instead of negative 2/5 in part B. Well, they will still give you full credit as long as you import it correctly. Now the thing is, there's usually a few little checklists, like you have to have done the derivative correctly in part B or something like that. You can't just say, okay, B, let's just make up dHdt as 6 and have no other work. There has to be something supporting it. But yeah, if you do something wrong, you can still get full points later on if you use that wrong answer correctly. We good? We good? We good? All right. Let's look at, we have 20 more minutes. Okay, I want to look at these questions, and when we have our free response quiz, where are they? This one. When we have the free response quiz, it's going to be something similar to these two, and also similar to the first one we did. There's going to be a little bit, there's going to be a table or something like that. There will be some theorems questions, and then rather than hitting you with the full related rates, it's going to be just a single part that has related rates. I'm not sure this one has any related rates in it. Oh yeah, it does. So let's look at this one. And these are problems. This one's from 2007. This one on the back is from 2011. And I think we've done parts of this 2011 one before, Ben and his unicycle. But I went through and I altered it because there were some parts we don't know how to do. So anything with an asterisk by it is my creation, using the same information, but I just created some other problems to go with it. So if you do decide to go online and look for the solutions, you can find the 2007 solutions online. Just know that anything with an asterisk is not going to be there. You'll be able to find the solutions for anything without an asterisk. So let's look at this first problem from 2007. Were any of y'all born yet? No? Okay. So 2007. See, y'all were, what, first grade? Maybe kindergarten? I've been teaching here for so long. If I stay here another 5 or 6 years, I may start actually teaching children of former students. I don't know. All right. So from 2007, we have a table. It says the volume of a spherical hydro balloon expands as the air inside is heated. Science says that makes sense. Science does not say that a perfectly spherical balloon makes sense, but we're ignoring that. This is a perfectly spherical balloon. The radius of the balloon is measured in feet, modeled by twice differentiable. That's important. A twice differentiable function, which means all theorems are fair game. T is measured in minutes, 0 to 12. The graph of R is concave down. R is concave down, so that means R double prime is negative, and that's the kind of connection you need to make. right? Whether or not we use it, I don't know. But we're concave down. Table gives selected values of the rate of change. Notice this is r prime, not r. So pay attention to stuff like that. The radius is 30 feet when t is equal to 5. So I'm going to make a note that my radius at time 5 is 30 feet. Now don't get confused. Of course it doesn't say 30 right there because this is r prime, not r. So pay very close attention to what you're given. Estimate the radius of the balloon when r is 5.4. So we're trying to estimate my radius at 5.4. That's our game plan. Using a tangent line. First thought. Good. We need a point and a slope. A tangent line at t equals 5. I need a point, and the point would be my r at 5, and my slope is going to be r prime of 5. Both of those should be absurdly easy to find. R of 5 is 30. R prime of 5 is 2. Right? And so I now need to write the equation of a line tangent using the point 530 and a slope of 2. Technically, well, here's what I want to do. I want to say y minus 30 is equal to 2x minus 5. Are y'all okay with that? I'm okay with that also, and I seriously doubt they would count that against you. I would be shocked. I would be absolutely floored if they did not give you credit for that. However, this is r as a function of t. So technically, it should be r minus 30 is to t minus 5 to be consistent with the variables that they've given us. That said, that is very, very picky and pedantic. I seriously doubt they would count off for that. You just want to stick with y's and x's? Yeah, no. All right, so we're trying to estimate r of 5.4 using that tangent. So r of 5.4 would be approximately, not equal, 2 times 5.4 minus 5 plus 30. And that will be measured in feet. I don't care what number that is. I'm not going to simplify that until they ask me a question that forces me to simplify it. We good there? What kind of question was that, by the way? Remember what we called that process? Linear approximation, using the tangent line to approximate the function values. That's linear approximation. Then it asks, is this estimate greater than or less than the true value of r of 4.5? What do you think? Huh? It's an overestimate. That's right. Why? Because it does say give a reason for your answer. Yeah. The over-underestimate question is a function is dependent on concavity. They tell you that r is concave down. If your function is concave down, every tangent lies above the curve. Therefore, this is an overestimate. And your reasoning is simply because r is concave down. You do not have to prove that r is concave down because they told you r is concave down. You just have to mention concavity. Don't say overestimate because the tangent is above the curve. That kind of begs the question, how do you know the tangent's above the curve? Well, because it's concave down. Good, good? Good, good. Number B. Estimate the value of r double, oh, that's C. Whoops. Estimate, there's no estimate. I need to read. Find the rate of change of the volume. Oh, this looks like related rates. I think I can probably do this in a new page. I don't think we're going to use part A at all. I hope not, because I'm not grabbing it. Where's my question? There he is. Okay, so same information. Find the rate of change of the volume. Find dv, and they do say with respect to time, so that would be dv dt when t is equal to 5. Indicate units of measure. And they give you the formula for volume right here. I told you most things with a slanted or a curved side, they will provide that volume. Anything with straight sides, you are expected to know. So my volume formula, 4/3 pi r cubed dv dt is 4 pi r squared dr dt. And we start plugging in. We're looking for dv dt. 4 pi r. Oh, when t is 5, what is my radius at 5? All right, that was 30. That was given. 30 squared. And dr dt is going to be r prime at 5, which is 2. Off the table. That was a nice one, wasn't it? That was nice. What would I do next? Very good. I'm going to put the units on and I'm going to quit. Feet cubed per minute. You should be able to clean that up, but you don't need to. There's no benefit to simplifying that. Good, bad, ugly? Not bad, is it? I like free response questions. Aren't they fun? Do you feel like you're building character? Whatever. All right. C. I created C. I was proud of myself. Estimate the value of R double prime of 6 using the data in the table, and then use correct units to explain the meaning of that answer in the context of the problem. Let's start by getting R double prime of 6. How would you do that? Well, we're looking at R prime. I need the slope. We'll do the slope from 5 to 7. Now you must show your work. You cannot just say negative 0.8 over 2. You can't do that. You have to actually show you're doing 1.2 minus 2 over 7 minus 5. Now, negative 0.8 over 2. Okay, I'm going to live dangerously. Negative 0.4. I know. I think I'm right, though. Then the tricky part. Use correct units to explain the meaning of that value. What does this mean? What does this mean? This one's going to be a little bit trickier because you might be tempted to try to interpret it in terms of the second derivative. Is anybody thinking concave down? Because I have told you if you're going to interpret derivative values, to keep it simple. If a derivative is positive, function increases. Derivative negative, function decreases. Well, this is second derivative, so you might be tempted to think R is concave down. But what does it mean if the measured radius is concave down? That's hard to wrap your head around, isn't it? So here's what I'm going to think. R double prime, it's the derivative of R prime, right? So if R double prime is negative, that means R prime is decreasing, right? I'm going to keep it in terms of a derivative. I don't want to go too far into my derivatives here. So if R prime is decreasing, well, what does R prime represent? Well, R prime would be the rate that the radius is changing, right? R prime represents, now R is the radius, so R prime is the rate of change of the radius. And it kind of says that here. The table above gives selected values of the rate of change of the radius, right? So there's your description. So the rate of change of the radius, and all of that is a big way of saying R prime. So R prime is decreasing at, and here we have to restate all of our values, decreasing at 0.4, not negative 0.4, because the word decreasing implies the negative. At 0.4 what? What would units be? feet per minute squared, right? We found the value of a second derivative. It's like an acceleration question. So the rate of change of the radius is decreasing at 0.4 feet per minute squared at time. I do this every freaking time. T equals 6 minutes. And once again, I made the exact same mistake I always make with these problems. Every time. Huh? Oh, okay, that was my cross was not very crossy. It's an approximation. The way I worded that makes it sound exact. We're decreasing at approximately. And again, I don't think that will count off on the AP exam, but technically it is an approximation. So it decreases at approximately 0.4 feet per minute squared. Yes, sir. R prime is decreasing at possibly. I don't like that because then what does R represent? Yeah, I like the words. I like the words, and I will look up some problems and see what the grading criteria was. I'm pretty sure that saying R prime is decreasing is not good enough. Even the reason it might be is because if all of your units, if everything else is correct, that may save you. But I think they're wanting you to, in a sentence, describe what the function represents. Good on C? Let's see what D is. There's a lot of work on this. By the way, free response questions usually don't have this many parts. I was getting a little bit carried away. I didn't want y'all to get bored. D. For 0 to 12, must there be a prime when a time, new page, yeah. Must there be a time when, did I not, son of a, let's go back. There it is. Okay. There, okay. Must there be a time when R prime of t equals 3? Justify your answer. First, it's a yes or no question, so make sure you answer with a yes or a no. What do you think? Yes. Why? Okay, it's intermediate value theorem. But before you use a theorem, you have to lay out the conditions that allow you to use that theorem. What's the requirement for intermediate? That's overkill. Minimum requirement. Continuous. We have to establish that R prime is continuous, which it is because they tell you that R is twice differentiable, which implies the continuity, right? But R prime is continuous on the interval 0 to 12, right? We know that R prime of 2 is greater than 3. R prime of 5 is less than 3. Therefore, R prime of t must equal 3 somewhere for some t on the interval 0. Whoops. I could narrow it down. I could actually say between 2 and 5. Now the question asks from 0 to 12, but 2 to 5 is sufficient. You good? Before you cite a theorem, you must establish the conditions. And I didn't do this on purpose. I'm kind of glad I did. Notice I never mentioned the intermediate value theorem. You don't have to name the theorem. You just have to explain basically how you know. If you know the name of the theorem, it helps out a little bit. But you don't have to actually name the theorem. Okay, good? Good. And then E, I think we can finish E. Explain why there must be a C such that R double prime of C is negative 2/3. What do you think we'll do on this one? This one's going to be mean value because we're trying to guarantee a slope of R prime, right? So the slope of R prime equals negative 2/3. The function R is twice differentiable, which means R prime is differentiable, and that's important. So we have to fish through here to see, is there a time when your slope is negative 2/3? Do you see a time where if I find the slope like from 0 to 11 or 0 to 12 or 2 to 7, is there at any interval with a slope of negative 2/3. Do y'all see it? Yeah, there is one. They're not going to ask this question if you can't use the mean value theorem. And so it's in there, and if you do the slope from 2 to 5, you're going down 2 and you're going up 3. That's a slope of negative 2/3. So R is differentiable and continuous on the interval 0 to 12. R prime is. Therefore, the mean value theorem says that R double prime of t must equal R prime of, and we're doing the slope from 5 to 2. R prime of 5 minus R prime of 2 over 5 minus 2, which is, it was 2 minus 4 over 5 minus 2, which is negative 2/3, for some t. We don't know where, but we know it happens somewhere on the interval 2 to 5. And there we're good. What do we think? Okay? All right. Tomorrow, we're going to go into antiderivatives tomorrow, but I will tomorrow tell you more specifically what to look at and what to study for the free response quiz. We'll do that next week sometime, but I'll let you know what it's going to be on in more detail tomorrow.